11 o'clock. So, all right, so I think we have 17 people who signed up for Mastering Physics. All right, and so, again, I urge you to do that. Okay, I'm gonna extend the date on that assignment, maybe a few more days, but apparently it's working because people are successfully joining. So apparently it works. Okay. All right. So we dealt with that business. Let me make sure I'm recording. Yeah, we're recording. Okay. So, all right. So again, as a part of that software, you have access to an e-text. All right, that's your textbook, and you should download that as soon as possible. All right, but today, as I promised on Monday, that we will go back through these slides and answer some of these clicker questions. Okay? So I'm not going to answer the question. You guys are going to answer the question. All right, we're going to skip that stuff. Skip all that. All right, that's the first question. So who wants to take the first question? Ask. I think that's the right answer, right? So we recall that inertia is a function of mass, meaning the more massive something is, the more inertia it will have. All right? And we all know that because it requires much more effort to stop something bigger in motion than to stop something smaller in motion. The same way it requires more effort to start something bigger in motion than to start something smaller in motion. So mass, all right? So we remember that. Inertia is a measure of mass. Okay? I don't necessarily like this one. We're gonna skip that one. So, the density of 1 kilogram of iron is less on the moon. First, anybody got anybody want to take this? Anybody got an answer for me? B? You say the same on the moon? Huh? What you say? You say B? Okay. Anybody else got a different answer? A. Why? Okay, that's good. That's a good observation. All right. It's B though, right? Because there's a difference between what? Mass and weight, right? Mass stays the same. So no matter if you leave the earth or not, your mass will stay the same, like I said, unless I do what? Chop your head off. Alright? But your weight is a manifestation of gravity. So it depends on how hard the earth is pulling on you. So when you go off and on the moon, the earth has it's not pulling on you as hard because you're so far away. All right. Let's see. A cart is pushed to the right with a force of 15 newtons while being pulled to the left with a force of 20 newtons. Come on, folks. Let's get it. We got this. This tug of war. Hey? Everybody agree with that? All right. Good. Hey. I think that's pretty straightforward, right? The equilibrium rule refers to, I'll just give you this one. This is vector quantities, okay? So what that means is that, so on the tug of war, the question you just gave me an answer to, right? If both of the forces were pointing in the same direction, then you would have got a different result, right? It's because one force was pointing in this direction, the other force is pointing in the other direction, so you subtracted the two. But if they're pointing in the same direction, you would have got a different result. That's because force is a vector, okay? Don't worry about that. We'll talk more about that later. All right. So, right, and I guess y'all, we seeing the answers right here, y'all, right? So, I mean, a correct answer is really nothing to me, okay? It's how you come up with that answer is what means everything, okay? Because on your exams, just letting you know that you're gonna have to solve problems and not a multiple choice or a fill in the blank or a circle the correct answer, okay? So you're gonna have to have some type of understanding, all right? You won't have 100% calculation exams, right? But there will be some calculation on there, okay? So the idea is, right? So here it is, right? So it says a bowling ball is in equilibrium when it is, right? Is at rest or moves steadily in a straight path. Everybody understand that? Everybody understand why the bowling ball is at equilibrium in both situations? Tell me why. Since you tell me what's similar about A and B.
I say because the bowling ball is equilibrium because you got pushed.
Well, it says what? Is at rest. So in this case, no, it's not pushed. Yes, ma'am. That's the key, right? A and B are the same because acceleration is 0. So it's at rest. Obviously, there's no acceleration. It's sitting still, right? But it says here what? Moves steadily. That means at a constant speed. That's like the earth moving right now, right? Moves at a constant speed. So there's no acceleration, so you feel no force because there's no acceleration. Okay? That's good. All right? Let's see. Now remember we talked about support forces, right? So when I put an object on a table or any kind of surface, in order for that object to sit still at rest, like we just talked about, right? then it must be at equilibrium, right? We just answered that question. Y'all just answered that question, right? Bowling ball is in equilibrium when it is at rest or moves steadily in a straight line, right? So this is at rest. My book bag is at rest, right? So that means it's not accelerating. But does that mean it is experiencing no forces right now? So what happened? Why is it not accelerating? Because if something accelerates, that means it has experienced a force. So what has happened to make this not accelerate?
It's gravity, right? It's putting it down so it's floating, correct?
Well, yeah, you're right. That's one force, gravity. But what else? Because if gravity was pulling it down, you would see it go down. Why isn't it going down? Because of the support, right? Look at this, right? Because of the support force, right? Now that's different. That's a spring. That's a different situation, okay? But this is the book, right? The book on the table. The book is being pulled down by gravity. That's gravity right there, right? This is the support force. So when I put something on top of a surface, right? That surface has to be able to put enough support back up on that object so that it is in equilibrium. Otherwise, what happens? If you get up on a table with a bad leg, and you stand up on it, what's gonna happen? You're gonna do what? Accelerate towards the earth. The earth is gonna pull you back towards the earth, right? That's gravity. Gravity is gonna pull you back, right? But if that table has enough support force to hold you up, there ain't nothing gonna happen. That's in everything, right? So if you think about things like a tug of war, right? There's one force pulling you down, gravity, and then in order for you to sit still here on Earth, right? There has to be a support force which is pushing back up. Otherwise, you would be accelerating. Just like if you jump off a building, there's no support force left there, right? So what you gonna do? Accelerate to the ground. All right. So I think I skipped that one. All right. That ain't nothing. All right. Let's see. The force of friction can occur. The force of friction can occur. Huh? Speak up. D? Well, we got it, yeah, right? All of the above, right? But, all right, so I experience friction in water. I'm asking you. You answered the question, right? You said no, you don't experience friction in water?
I didn't answer the question.
Oh, who said D? Oh, that was you. Man, I thought that was you. I thought I saw you say D. Crazy. So we experience friction in water? Yeah? How about in air? Yeah? Can you explain it a little bit? What we call it? You can explain the one in water if you wanted to, but what about air though? That's the easier one, right? What do we call the friction of air? Air resistance, right? Air resistance, right? Just like if you're in water, then it'd be something like drag or something, right? The drag, right? We even have drag here on Earth in air, right? You gotta go fast enough though, like a race car experiences drag. An airplane experiences drag, right? A lot of different things. But it's all forms of friction, okay? And it's intended to retard your motion, okay? Somebody give me a sheet of paper and start circulating that roll. Oh, I got it. Yeah, because I got like 43 people in this class, right? And, you know, I think I've never had more than, it's probably the most I've had. And, you know, I recognize, well, I don't recognize some faces, so let's make sure everybody's on the same page. All right? Because there will come a time when we all have to reckon for what we have been doing, where we have been, and how we spend our time, right? Because I can't keep up with that. Only you know how you do that. All right? So, let's keep moving forward. All right. So, let's see. This is a good one, right? When Nelly pushes a crate across the factory floor at a constant speed, the force of friction between the crate and the floor is C, right? C. Right? Equal and opposite to Nelly's push. So if the force of friction is equal and opposite to Nelly's push, is the box in equilibrium or not? Is it in equilibrium? That's the question.
Yes.
Why?
Because it's at a constant speed.
Because it has constant speed. Yes. Absolutely. The box is in equilibrium. There are two conditions for equilibrium. We just went over them, y'all. We just said it's either at rest or at a constant speed. Okay? So a lot of this is about listening. You understand what I'm saying? Not mathematics. It has nothing to do with math. It's about listening, comprehension. Right? And sometimes I get it, you know, like if we're not comfortable with science and things like that, it take a little time, especially if you hadn't had a science class in a few semesters. Okay? But it's really, the answers are in everything I say. Okay? All right. Speed, right? The average speed in driving 30 kilometers an hour is the same average speed as driving what? D. Who said D? So how did you come up with that answer? Just multiply it by 2. Multiply 30 over 1 by 2 over 2. Right? All right. Let's skip that. All right. An automobile cannot maintain a constant speed when what? Come on, y'all. Huh? Yeah? Both of them, right? Both of them, right? C. Right? But, of course, this is what we said that what? Constant speed means what? Zero acceleration. So, of course, that's an answer. Right? But right here, rounding the curve, right? Because it's a vector, because the force is a vector, right? When you go around a curve, you're changing direction, okay? And when you change direction, which we really haven't gotten to that point yet, but whenever you go in a, I mean, y'all know this because we all are human beings and we live on this earth, right? Anything that travels in a circle, right, eventually will crash into the center of the circle because it is accelerated towards the center of the circle. Anything that travels in a circle. If it does not crash into the center of the circle, then that means there is another force that's stopping it from crashing into the center of the circle. Right? Prime example is what? What do we do on Earth? Huh? Yeah, we rotate. But what we do this too, right? Go around the sun, right? We travel in a circle around the sun. I just said anything that travels in a circle will do what? Crash into the center of the circle. So why don't we crash into the sun? Because there is another force which pushes us away from the sun at the same time. Okay? That's why. So that's why when you travel in a circle, you have an acceleration. Because your direction is changing. It's constantly changing. All right? Good. All right. We talked about this. How much time we got left? We talked about this. We talked about this free fall. We talked about this on Monday. Free fall, right? Free fall, an object gains 10 meters per second, right? Remember when we went through the chart at the end? Every second we gain 10 meters per second, right? We dropped it at 0, 0. After 1 second, it was at 10. After 2 seconds, it's at 20. 3 seconds, 30, blah, 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 right? Falling object gains 10 meters per second. Each second it falls, its acceleration is what? B, right? 10, this is a what? What do we call this? Meters per second. You on the track team? Okay, same difference. Meters per second. When you run, when they clock your speed, a lot of times they're doing what? What is it, 40 meters? And they measuring it in how, in what? Seconds. So this is a what? A what? I just asked you, I said, whenever they clock your what? Speed. I said, they measuring it in what? Meters. You run the 40 meters, and they measure it in seconds. So this together is a what? A speed. It's like miles per hour. Right? We're accustomed to miles per hour from our car, right? We're driving in the car, speed limit, all that, miles per hour. But that's just a unit, a different unit of measurement. Okay? Meters per second. This is meters per second. That's very different from this. This is an acceleration. And so we're going to have some practice with that. And you're going to get a chance to work with those units. And maybe you'll get a better hold of it. All right? So let's see. A free-falling object has a speed of 30 meters per second at one instant. Exactly 1 second later, its speed will be what? I got an answer? Think about it. 35?
60.
That's all those are both of those are close. No, that's more, right? More than 35, right? Why? Because what? Because we said that in free fall, things gain what? 10 meters per second. So, you started out at 30 meters per second. And it asked, it said, well, after 1 second, it should be at what then? After 1 second. It gained 10 meters per second every second. If it's at 30 meters per second and it gained 40. Yes, sir. 40. Right? But that's also the same as saying what? More than 35. Not 35. That's wrong. Actually. Right? Technically, you're wrong. Right? So yeah, so that's how you look at that, right? We go 10 meters per second after every second of falling in free fall. Your speed should gain 10 meters per second. Okay? So that's the understanding. The distance fallen by a free falling body. What's the answer? B. Who said B? You said B. Okay. Why? Explain to us. Or explain why you said B.
Or maybe C.
Don't change it. No.
You said B.
Yeah,
I would
you're
say
right.
C only because I'm thinking it's the distance from the Earth, right? That's why I would change it.
No.
So it's the distance from where.
From its
From the
starting
start.
position. So if it starts up here, when it falls, it's the distance from where it started.
Okay. So why wouldn't it be the distance from like the Earth?
Because it's from the starting to the stop position.
Okay.
Start, stop. Now if we started on Earth
Mhm.
and then we went like that, then that'd be the same thing. But we're talking about something we're talking about free fall, right? Yeah,
Mhm.
free falling. Free falling means that it's going back to the Earth. It's being pulled to the Earth by gravity. That's what free fall means,
Okay.
right? So we have to go from the starting is up here. Eventually, it's going to end up what? At the Earth.
Yeah.
That's gravity. Okay. All right. So yeah. So the answer is right. B. Increases each second. Right. So why is that? Anybody?
Is it because like you gotta account for the body weight as well as they told you?
Well,
It's just
I mean, you gotta. Well, I mean, the weight. No, it had nothing to do with the weight, right? Huh?
The gravitational pull.
Gravity is accelerating it. Yes. That's it. That's it. That's the answer, right? Gravity makes it speed up. That's why it's increasing. Increases each second. Gravity is increasing what we say. It accelerates the free falling object. So that means it increases its speed. So if I increase speed, then I do what? Cover more distance. All right, I think that's it, folks. So, so that's all the slides. All right, so hold your horses. That's all the slides. Yeah. So how many people signed up for the master? Yeah, Mastering Physics. Are you logging on to the Canvas page? What's not working? All right, because I need to see. Like I said, we got 43 people registered in this class. 43. And we got 17 people registered in Mastering Physics. All right? So, maybe we can spend a few minutes for those of you who are not registered. All right? And so let me just explain something to y'all, right? Like, you know, I'm not a micromanager type, right? So I'm not gonna run behind you and try to convince you to do things. Not gonna do it. Okay? I tried it before and it backfired. Okay? So I'm urging you to go ahead and get that task completed. All right? Because you got, not only is your book there, but it's also, you're also gonna have your homework and stuff there. Okay? So, all right. So, do I have my my roll? Everybody sign the roll. So everybody in here is registered in Mastering Physics.
I withdraw for no show, but I've been here.
Oh, okay. And make sure you sign the roll. What's your name?
Jasmine.
Okay. Oh, you need to sign.
Yeah.
That's right, I might have
That's on the back where you sign. I'm gonna put this on.
Go ahead and fill it out first. Yes, sir.
Yeah, hold on, I got this.
You said ask a student. Ask one of your fellow students. Like I said, like I told you, like I tell him, you do better asking one of the other students. Yeah. You registered already?
So, like when it's picking up, so I'm gonna click open. Like it's not opening.
You can see if we registered because I registered last
They
night.
should send you an email.
Got email?
Yeah. Oh, you got it? Okay.
No, I don't got no email.
Me, Miracle Williams.
Say what now?
Miracle Williams.
You say what?
The enrollment expired.
Enrollment expired? All right, let's do this.
You-
This is the list right here. What you want to see? Who you want to
My
see?
name.
What's your name?
Miracle.
You on Miracle Williams?
Mhm.
I saw.
Okay, I'm good.
Should be good. They said that
What was that? Oh, the enrollment.
no problem.
We're gonna take care of this by Friday. If you can't get this by Friday, I don't know what to say. So it might take a little time though the other day. Remember like last time?
Do you
So
know,
yeah.
the CRM?
Mine's is not loading.
CRM.
You gotta look.
Oh, okay. You got the form to sign?
So I don't get in this way and take pictures.
Oh, you sign, sorry.
I might just have to do it in the computer
I'll be here.
lab. Okay, thank you. Thank you.
Okay. Yes, I would suggest you can always scan it and send it to me. Scan it and email it to me.
If not, I can sign it and bring it back.
Yeah.
I'll be home.
So we gotta sign up for this because class got sent up on campus.
Whenever you get put back on campus.
So when I get put back, you gonna I can sign up for the master.
Yes, sir.
I'll try to get that done today.
Ah,
The fifth,
what's your name? Oh, I got 24. Okay. What is your last name? Lee. So what did happen?
It let me in this time.
It might just take a little time.
Friday.
I know you've been trying.
Yes, I
Oh, what's your office number?
Well, my office in the building. They about to tear my building down. I don't have no office yet.
Oh, alright.
Yeah. So just email me.
Alright, for
You know
sure.
what I'm saying?
Alright.
You know how to get how to get the emails?
Yeah, I got you because I sent you the excuse letter before.
All right. Got it.
No, he's supposed to sign on the back. He put his name right here. And he signed on the back.
Where at?
Okay.
Oh, what's the
And it says if it's
Oh, all
approved.
right. Yeah, yeah.
Is that when, the road, is that, did I miss anything when I
This is the
went
roll
out?
right here.
Oh, I signed it.
Okay, thank you.
Sorry about that.
Yeah, no problem.
What is this? Oh, Horatio. Yeah, I ain't see you on the road.
No, I
I
signed
look
it.
over and over. I say Horatio.
I signed it in a pink, on the pink ink. I can't touch it inside.
No.
2525.
All right, y'all.
Thank you.
Yep.
Have a nice day.
Yes, sir.
My boss,
Yes, sir.
please, he said,
Talk about, yeah. Print this page. You're done. All right, so you should be in. What's your name?
Jude,
Let's refresh
CH,
this. Let's refresh this. 25. That's probably you.
that's me. Praise the Lord.
Chuck.
Yay! Thank you.
Yes. You from Nigeria?
Listen,
Yes, sir. I had another student named Chuckwu from.
Chukwebuka.
Oh yeah, you Chuck. How you say it? Chuckwu.
Chukwebuka.
Chuckwu Buka.
Or you can call me Jude.
Jude.
Jude, yes.
Okay. Yeah.
Thank you, sir.
All right.
Hey, sir, I want this Do you prefer making notes in the class or read through the computer?
I'd say pay attention mostly. That's for me in my class. I say just pay attention, right? Because what I'm saying is have you picked up on the fact that I'm recording these and I have them on your canvas, so you can go back
Yeah.
and look and listen if you want to listen.
Yeah, listening is good.
Yes.
Thank you, sir.
Yes. And you have access to the slides, so you don't need to really take notes. All of the notes are there.